Hello, I'm Francisco Oliveira, and we are going to talk about coordinate systems. Once the surface of the Earth has been flattened, now we want to locate all the points based on their coordinates. So for that, we need to agree on the origin, where we're going to start measuring the coordinates, and the directions of the axis. So there are some coordinates that are well known. That is what we're going to talk about here. There are going to be two types of coordinate systems. One is one system is the geographic coordinate systems, which have to do with latitude and longitude, which is something that we are aware of. And the other ones are the projected coordinate systems that are based on a mathematical algorithm to flatten the surface of the Earth, just like we were mentioning before. The geographic coordinate systems are not exactly a projection. We tend to call it a projection geographic, but it's not exactly a projection in terms of there's no lamp, film, and screen as we mentioned for a projection. So let's see what geographic coordinate systems stands for. So we're going to have the latitude and longitude. The longitude is measured east and west from Greenwich, which is a location very close to London. Everything that is to the east is going to have a positive longitude, and everything that is to the west is going to have a negative longitude. So you can have a maximum east longitude of 100 and plus 180 degrees, and the minimum would be on the west side, which would be minus 180. So 180 positive, 180 negative, that is going to cover the entire Earth. The latitude is going to be measured from the equator, and you're going to have 0 at the equator, and then you measure the angle with respect to the equator, like you have here, this phi angle. This is going to be the latitude, and that is going to be 0 at the equator and 90 degrees at the North Pole, or minus 90 degrees at the South Pole. So to summarize, the longitude ranges from minus 180 to plus 180, or we can also say 180 west to 180 east. Latitude ranges from minus 90 to plus 90, or 90 south to 90 north. Just to have an idea of what 1 degree means, of any amount of degrees means, notice that when you travel north-south along a line that connects the two poles, these are called meridians. When you travel along a meridian, this distance, in this case AB, and this point looks at the equator, but it doesn't have to be at the equator. It can be anywhere. We're assuming a sphere here to simplify the math. So when you travel north-south or south-north, the distance AB is going to be equal to the radius of the Earth. This is the center of the Earth. It's going to be the radius of the Earth multiplied by the angle, in this case, the difference in latitude, in radians. When you travel east-west, it depends on the latitude. At the equator is going to be the maximum difference. You can see the distance between these two meridians is the biggest at the equator, but as you move north, it is reduced and reduced and reduced until it's actually 0 at the North Pole. Why is that? Because now the distance CD is going to be equal to the radius of this circle, the circle that corresponds to this parallel, and it's going to be this little r, not the big R, which is the radius of the Earth is going to be this little r, which is actually the radius of the Earth times the cosine of the latitude. And that is going to be multiplied by the angle in radians. So this cosine of the latitude, when the latitude is 0 at the equator, the cosine is going to be 1. So that is going to be the maximum length. When as the latitude increases, the cosine decreases. By the time it gets to the pole, the latitude is going to be 90 degrees and the cosine is going to be 0. So that is why this distance CD is going to be equal to 0 if you use this parallel up here at the North Pole. Specifically for 1 degree, we would like to know what is 1 degree. We're in Austin. What would be 1 degree in the north-south direction and in the east-west direction if you are traveling from Austin north or from Austin east? Just this drawing, which is to scale, is showing you that it's going to be a longer distance in the north-south direction than in the east-west. We are going to assume that the shape of the Earth is spherical and that the radius of the Earth is 6,367 kilometers. So 1 degree is going to be, in radians, is going to be equal to pi divided by 180 degrees, which is 0.0175 radians, and the number continues. Now, along a meridian that is north-south, the distance is going to be the radius of the Earth, 6,367 kilometers times 1 degree, which is 0.0175, that is 111.4 kilometers. In the east-west direction along a parallel, CD is going to be equal to R, the radius of the Earth, cosine of the latitude of Austin, which in this case is 30 degrees, 0.2672, times the angle, which is going to be 1 degree. So we have 6,367 kilometers times the cosine of 30.2672 times 1 degree in radians, which is 0.0175. That is 96 kilometers. So if you move from Austin north-south, 1 degree is 111 kilometers. If you travel east-west, it's going to be 96 kilometers. Notice that the distance along a meridian does not depend on the location, so it's the same amount regardless of where you are. It could be Austin, it could be Miami, it could be in Rome, Madrid, Beijing. It doesn't matter where you are. It could be northern hemisphere, it could be southern hemisphere, it doesn't matter. Traveling 1 degree along a parallel depends on the latitude. So it's going to be longer at the equator, and as you move to the North Pole, it becomes shorter. So it's going to be longer in Austin than it would be in somewhere in Minnesota. And it also doesn't depend on the longitude. So the longitude of Austin, 90 degrees, 0.7431, does not affect this calculation. So that is about geographic coordinate systems. So now we're going to talk about projected coordinate systems. So step number 1, we have the curved surface of the Earth on an ellipsoid. We flatten the surface of the Earth, and now what we want to do is we want to define an origin, and we want to define our axis X and Y, most likely perpendicular. That's what we've learned from math. So we want to define our axis so that every point on the surface of the Earth can be located with an X and Y coordinates. we're going to use three well-known coordinate systems. Universal Transverse Mercator, which is also known as UTM, a state plane that applies only for the United States, and Texas statewide mapping system that applies to Texas. Universal Transverse Mercator is going to be a transverse cylindrical projection. You may want to check what a transverse cylindrical projection is. So I'm going to go up in the presentation just to refresh your memory. So this is going to be a transverse cylindrical projection. UTM, Universal Transverse Mercator, is going to define a cylinder that is going to be tangent to the surface of the Earth along a meridian. And along a meridian, that meridian, the projection is going to be perfect because the surface of the Earth barely touches the cylinder, so it's going to look perfect along this meridian. But as you depart, there's going to be more and more distortion. So this person, Mercator, said, we are going to tolerate distortion up to 3 degrees on one side and 3 degrees on the other. Now you know what 3 degrees are. 3 degrees is going to be more or less 333 kilometers at the equator. So this is going to cover at the equator a distance of more or less 660 kilometers. So Mercator said, we're going to define zones, and at the equator, this distance is going to be very close to 666 kilometers, a little bit more. So he divided the Earth into 60 zones, and each zone is going to cover 6 degrees. So it's going to define a meridian in the middle, 3 degrees to one side, 3 degrees to the other. And all these zones were numbered. So zone number 1 is going to be here in the middle of the Pacific, and it's going to cover 6 degrees. And then the next 6 degrees are going to be zone number 2, and so on. Texas here is going to be, Central Texas is going to be zone number 14. By the time we get to what is called the prime meridian, this is going to be zones 30, to the east, zone 31, and the last is going to be zone number 60. In order to avoid numbers that are too big or negative numbers, it defines what is called a shift, so that all the coordinates are going to be positive. That is why you're going to have UTM projections, not only for the 60 degrees, 60 zones, but also for the northern hemisphere and the southern hemisphere. The units are going to be meters. So when you use an UTM projection, you just say the zone and a hemisphere. So for example, for Central Texas, a good projection would be UTM zone 14, northern hemisphere. All the parameters of the cylinder, where the cylinder should be located, all that is already determined by the fact that it's going to be zone 14. All the parameters are already prepared as a package. Universal Transverse Mercator is used almost all over the world. In the United States, it's less used, but it is also used. In Texas in particular, we're going to have zone 13 for West Texas, 14 for Central Texas, and 15 for East Texas. So if you want to prepare a map of the entire state of Texas, probably UTM is not a good projection because the range from El Paso here to the Sabine River on this side, it covers more than 6 degrees. So if you use 14, you're going to have probably too much distortion in East Texas and also in West Texas. So UTM is not recommended in this case. But Texas is such a big state that it doesn't matter which projection you use, there is always going to be a large amount of distortion. Another projection is called state plane. State plane means official projection. Let's say each state is going to have a different projection. But there are states that are so big that they needed more than one zone. Texas specifically, you can see they decided to divide it into 5 zones. North, which covers the Panhandle, North Central, Central, South Central, and South. In Texas, these zones expand more or less east-west. That means that in Texas, the projection that is used is going to be a conic projection. Areas that are more north-south, like New Mexico, Arizona, Nevada, Idaho, Missouri, Illinois, Indiana, Mississippi, Alabama, Georgia. These states most likely use, if not UTM, they are going to use a transverse Mercator projection. Those are good for north-south zones. But for east-west, they are going to use a conic cylindrical projection. Not all the zones that are defined as horizontal are going to have exactly the same conic projection. Each of them is going to have different standard parallels. So it's not enough to say this is going to be a conic projection or equal area conic projection or conformal conic projection. That is not enough. You have to say what the parameters are. And most likely the standard parallels here are going to cross the area. So the standard parallels here are going to be somewhere in the area, the Texas South area, and here in North Dakota North are going to be somewhere up here. So the standard parallels are different. The cone is going to be different. The projection is going to be different. All counties belong to one of the zones and only one. No county belongs partially in one zone and partially in the other. So you can find which is the zone for your county, Travis County, for example, where Austin is going to be in Texas Central. There are a total of 124 zones, and in most cases, the east-west zones use Lambert conformal conic, or they could also use Albert equal area, but most of them use Lambert conformal conic. And the north-south zones most likely use a transverse Mercator projection. So once again, the term state plane means official, and what is official in Central Texas is not official in, for example, East Georgia. You can call it official, but they are going to be different projections depending on the zone. For the entire state of Texas, the entire state, probably the best projection is Texas statewide mapping system, which is a Lambert conformal conic projection. It preserves the shapes. And I show here where exactly can be found in ArcGIS Pro. So this is going to be a Lambert conformal conic, so it's a conic projection. That means that the standard parallels are going to be here and here. As you depart from the standard parallels, you're going to have more and more distortion. So that's why the standard parallels are within the northern boundary of Texas and the southern boundary. And this is going to be the central meridian. So that everything is going to be tilted, let's say, counterclockwise on the east side and clockwise on the west side of Texas. So this is another projection that is used for larger areas. The advantage of a state plane is that since it is used in smaller areas, then there is less distortion. The bigger the area you want to project, the more the distortion you're going to have. In a map of the entire United States, you're going to see some funny shapes. If you want to project the entire world, it's going to be very, very distorted. But if you want a map of the whole world, then that's what you're going to get. So that's about coordinate systems.